Hello, ladies and gentlemen. Today we are going to talk about ideal gases. Before we get to talk about ideal gases, just a couple housekeeping items. Um, the exam, extra credit, is due today at 11:59 p.m. So if you want those 4 extra credit points, please work on that. Please try to get that in by 11:59 p.m. Again, those questions are going to be either right or wrong, and we've broken them up, and you can see on the assignment, you can see the new point values that I posted on those, so if you're concerned about how many points each part of a problem is going to be. Also, the exam grading is going along, and those grades should be ready, and I'll be able to post those on Tuesday and release the solution and all that information on Tuesday. The reason I wait till after the exam extra credit is because I want you to kind of have this week period where you're going to be working on that exam, and then on Tuesday we can just release it and say, okay, here's how it should have been, and so you can look at the solution and everything and try to understand where we are there. And then I'll be posting a survey for the class so you can give some feedback and how we can improve, or some things that are working well about the class that you're enjoying, and we can move on with that as we go and work towards exam 2, which is in the second week of October. We're coming up closely to that. Things are just flying by here in thermodynamics. But I think that's it. If you have any questions, please don't hesitate to ask or come by my office hours. Remember, it's every day, Monday through Friday, from 2:30 to 3:30 in my Zoom room. Okay, so today we are going to extend our talk about the ideal gases. And remember what we talked about on Friday. We said that if the compressibility factor, Z, is equal to PV over RT, and if this compressibility factor is equal to 1, then we're going to assume the gas, or we're going to say the gas is ideal. Now, we could do this for every gas, every problem that we have. We could say, okay, let's find out if this gas is ideal. But that would take us some time. So we're going to make an ideal gas assumption, or we're going to follow an ideal gas model. Now, whenever we follow a model or give an assumption, what we should do is always verify the assumption at the very end. That's the proper way to do that. What I'm going to tell you in thermodynamics is every time we see a substance that is a gas, air, carbon dioxide, carbon monoxide, oxygen, nitrogen, argon, helium, all those things, the assumption of being an ideal gas is going to be a good one, and we don't need to go back and check that. But it should be there. Whenever you make that assumption or that model, if you were doing a formal problem, you were going out and really working on making sure that you have this big, huge problem, and you make these assumptions, you always need to go back and verify your assumptions, or verify that your model works. You can't just do it and just hope for the best. That's always that's the right thing to do. So we talked about the ideal gas equation. PV is equal to RT. This is one of the ways we can model ideal gases. It's the easiest way to model ideal gases, but there are other ways to model ideal gases. There are other equations that they can use. We prefer this one because of its simplicity. And remember that this pressure must be an absolute pressure, and this temperature must be an absolute temperature. That is important. That is very important. And I promise you that whenever I give you temperatures on the exam, I will not give you absolute temperatures. I'll give you relative temperatures like Fahrenheit or Celsius, because that's what we use in everyday life. And you're going to have to remember to put it in an absolute temperature when you go into this equation. Okay? So let's talk about this ideal gas model. Whenever we follow the ideal gas model, and again, I'll put it for air, carbon dioxide, carbon monoxide, nitrogen, oxygen, what do I want to say, helium, argon. Whenever we follow the ideal gas model, what we're going to say here is the following: that specific internal energy depends on temperature only. Okay? And the same thing is for enthalpy. It depends upon temperature only. So remember, we need 2 things to set the states. For ideal gases, we only need really 1 thing to set the states. The other thing is, first is we're saying we're going to follow the ideal gas model. That's thing one, and thing two is going to be the temperature. That's all we need. Okay, and so that's important. So here, let's talk about this model. We talk about PV is equal to RT, and now we're going to say that the internal energy is only a function of temperature. Now, look, I'm just putting this as a function of temperature. U as a function of temperature. I'm not saying U times T. I'm saying U as a function of temperature. And enthalpy is also a function of temperature. Enthalpy is going to be equal to U plus PV. Okay, U plus PV. All right? And we know, because of our ideal gas law here, this ideal gas law, that PV is equal to RT. So for ideal gases, we can write this as U plus RT. That's a unique thing that we can do for ideal gases. Okay? Now, when we go and we make that model, remember, the model, the ideal gas model, is going to be a little bit away from reality. We're not looking at it as perfect. We're not trying to get the exact number. We're going to model it as there. We're taking in, we're assuming the compressibility factor is 1, or it's pretty close to 1. And once we do that, we are coming a little bit away from the correct answer. Okay? And so whether or not to apply the ideal gas model is depending upon you and your choice about the acceptable error in the calculation. Now, I'm going to tell you, the ideal gas model is a really, really good model. It's going to give you a very small amount of error, so we're really good with, we're really okay with using it, because gases often approach ideal gas specifications. Okay, so again, when do we use the ideal gas model? When Z is equal to 1. What are we going to say there? You know what? I think it's good enough. That's really what we're going to say. And we're going to look at, for ideal gases, we're going to look at them in the tables. And so let's look at the tables. I'm going to open up here, and hopefully my document camera works. Let's see if it works. That works. The document camera, we're going to go to our ideal gas tables. Okay, so now we have a whole bunch of other tables that we're going to be able to use today. This is exciting. It's like Christmas. We get to open up things and figure out what's going on here. Okay, so we already dealt with this. The ideal gas specific heats of some common gases: air, nitrogen, oxygen, carbon dioxide, carbon monoxide, hydrogen. That table we've already talked about. We can go to the next page, and we talked about these ideal gases, C sub P. But now we're going to go to this, table A22, ideal gas properties of air. Okay, so for air, it's its own table, and we're only going to be using the first 3 columns here. This column, S degree, and PR and VR, these things aren't eligible for us right now, only the first 2 columns. And note that this number is going to go from 200 all the way down to 440, and then it's going to repeat over here. Here's going to be 450. Okay, so it's going to go down here. There's 2 columns of data on every page. And we're going to be given the temperature and an enthalpy and internal energy. Now notice here, in our first tables, enthalpy came after internal energy. Now internal energy comes after enthalpy. So remember that these order of these has been switched. So also know, all I need to know is one thing, and I can set the other 2 things in the table. So if I know its temperature is 210, I know that the enthalpy is 209.97 and the internal energy is 149.69. If I find that the internal energy is 192.60, I know the temperature is 270. Anything works here. I can go to my next page, and it's going to continue on with this. We're going to go on to 750, and then the 1300 all the way down to 2250 for air. Okay? Again, we're not going to use these last 3 columns. Now, we're going to go to the next ideal gas properties, and now we're going to have a table for carbon dioxide, carbon monoxide, water vapor, oxygen, and nitrogen. Now, water vapor is an ideal gas in only specific situations. So again, we're only going to use carbon dioxide, carbon monoxide, oxygen, and nitrogen right now. Water vapor, again, we'll get to that really later on in this class, but we're going to work more with these 2 columns. And you will notice now that they are going to give us enthalpy and internal energy. There's a bar over this, and then units are going to be kilojoules per kilomole. So here's where that on a molar basis is going to be given out. So make sure that you are understanding that, how to go from a molar basis to a mass basis. We'll do some examples on that to make sure you understand. Temperatures given in both columns here, temperature here and temperature here, just so it's easy to use the table. And we go on and on, table A23. So those are the tables that we're going to use for this material. Table A22, A22E, table A23, A23E that we're going to be dealing with. And these tables are created with the ideal gas, if you say ideal gas model in mind. They're created with that model in mind. So we can use these and be very comfortable with having really good values. Okay, let's end this video here, and we'll move on to some other topics in just a second.